Okay, so let's go back to the slide. So we started talking about exponential families, and to briefly remind you, an exponential family is a parametric family of distributions such that the density has this exponential form. Density has the this form, and there are these parameterization function and the sufficiency statistic function that map your parameter space and your observations or sample space into RD, and then you form this inner product. And then there's this underlying measure, nu, and an edge here, which can be absorbed into nu, and this density is with respect to that measure. And then there's this log-partition function that can be computed given the other ingredients. So this guarantees that the density actually integrates to 1. And not all values of the parameter from your original parameter space might lead to a finite A, and the set of all thetas that lead to a finite A usually is the parameter space of interest for the exponential family. When we started talking about these conditions, so that sort of what I call actual parameter space is the set of all thetas such that A theta is finite. And I'm going to assume that eta omega naught, this is going to be a subset of RD. D is the dimension of the family. So we're going to assume that this is an open, has an open interior, or in some cases it is open. And furthermore, we are going to assume that the sufficient statistic, the coordinates of the sufficient statistic and 1, they're linearly independent, in the sense that I can't write a linear combination of them and set it equal to constant, and that would hold everywhere under the measure and the underlying measure. So under these two assumptions, E1 and E2, the model is called full rank exponential family. And we talked a little bit about the implications. So E1 generally prevents these parameterization functions to satisfy a non-trivial constraint, and we discussed this a little bit in the office hours. It's not a precise statement, but it's preventing cases, for example, where you have like a curve. This is the image of omega naught under eta, and you don't want this to look like a lower dimensional subset or lower dimensional subset of RD. You want it to be a full dimensional object. Whereas these curves or lines, things like this, they don't have full dimensional, say in R2. And then E2 prevents unidentifiability, meaning that it prevents the case where you have so identifiability. Again, to remind you, means that if theta 1 is not equal to theta 2, then the distributions are not equal. So this is key in models being well-defined or valid from a statistical perspective, or at least the parameter of interest be reasonable or estimable. Otherwise, we can't really estimate the parameter. Okay, any questions about this?
I have a sort of question or comment. So in a definition of exponential family, if h of x is just a constant function, then we can actually conclude that t is minimal sufficient, right?
We're going to talk about this. Not necessarily. It doesn't have anything to do with this per se. But we're going to actually prove now that t is minimal. And in fact, under the full rank assumption, it's going to be complete. It's a good question. Let me show you.
Okay.
It's just, no problem. It's just very timely. So here we will prove it actually. So just before doing that, I'm going to have two very simple examples. So suppose you have a Bernoulli model, and you can write the Bernoulli model like this. So x here takes values 0 to 1. And here I'm representing a binary random variable as having an exponential family with two parameters. So as a two-dimensional exponential family, you can easily see that these components of the sufficient statistic, they satisfy a trivial linear or affine constraint. So this means that this formulation violates E2. And if it violates E2, it means that the parameter is unidentifiable, and you can verify easily that not both of these parameters are required. So you can combine, because it's just the whole distribution is determined by just one parameter. The other one is determined by normalization. If you include these two parameters, then there are cases where the combination of the two would lead to the same distribution for different values of theta 0 and theta 1. And so you can easily verify. I think this might have been one of your homework problems. So this is easy to verify. The other example, for example, if you have a continuous, let's say omega is r, and then you define these parameterizations like this, then the interior would be empty and you'd violate the full rank assumption. There are other examples as well you might see. But if you rule these out, questions about this? So if you roll these out, let's say if I work with a full rank family, then in fact, it turns out that in a full rank family, T is complete. And this is the general result that I mentioned previously quite often. Was there a question? So this result you can use to deduce completeness in many examples of interest. And in fact, I'm not going to show completeness. I'm gonna ask you to believe this, and I'm going to just show the minimal sufficiency, which is a weaker statement. For the completeness, if you have thought about this in your homework problems, the completeness would be a little bit more technical, but essentially it reduces to an inverse Laplace transform argument. So you want to show that the inverse Laplace transform is unique, basically, something like that for your measure, for the measure that you're looking at. And this the complete full rank assumption is all you need. So let's see minimal sufficiency. So by factorization theorem, we know that T is sufficient for the whole family. Then we are going to use that result that we borrowed from the layman's book. So if we know T is sufficient for the full family, and we can show that T is minimal sufficient for a subfamily, then we know it's going to be minimal sufficient for the entire family. So that was one of the results that we had. And so what I'm going to define is a subfamily, just pick theta 0, theta 1 up to theta d to be a subset of omega. And then let eta I be eta of theta I. The way that I'm going to construct this set is to make sure that when I subtract eta I from eta 0, so eta 1 from eta 0, eta 2 from eta 0, eta d from eta 0, I'm going to make sure that they're linearly independent. And the assumption E1 is going to give us that. So if I have a set which is full dimensional essentially, so this is eta of omega naught, by assumption the interior is non-empty, so I can pick one point in the interior. And then there is a little ball around it that's entirely inside the set. And because the ball is full dimensional, I can sort of embed an entire coordinate system, full dimensional coordinate system. So I can, if this is a subset of RD, let's say R3, for example, here. Then I would have eta 1 here, eta 2 here, eta 3, and I call this origin eta naught. Then I would have eta 1 minus eta naught, eta 1, eta 2 minus eta naught. And the other one, these three would be linear independent. So they basically would be a basis for, could be a basis for the R tree, right? So I can make that construction. So that's where the non-emptiness of the interior comes in. I can embed a full dimensional little ball, and so you can take eta 1, eta 2, eta 3 sufficiently close to eta naught. So eta 1, eta 2, eta 3 sufficiently close to eta naught. So for example, they're in a ball of radius epsilon, centered around eta naught, such that they lie in that, and then in that ball I can just make them, let's say, all orthogonal, all these. So these are can be made to be linearly independent. Okay, so once I have that, I can add a page here. So once I have that, I can form these. Let's say I'm doing it with just theta 1, theta 2. For the sake of argument, we can do it for the general case. And then I have eta 0, eta 1, eta 2, eta 3, right? This is just eta of theta 0, eta of theta 1, and so on. So what I'm going to do is I have p theta of x is e to the eta theta t of x minus a theta. I'm going to ignore h for simplicity. It doesn't, actually, let's have it. So if you do p theta I divided by p theta naught, then you would get e to the eta theta I minus eta theta naught, and then t of x minus a theta I minus or plus a theta naught, and then the h's cancel out. Okay, and so this is eta I, this is eta naught. And I can write this as just, so what I would do is I form, so this would be by our result minimal sufficient. So the family has common support, everything is sort of fine. So this up to D here, D is, let's say 3, 0, 1 up to D. Well, actually not 0, it's just 1 up to D. 1 up to D. D here is equal to 3, for example. So this is minimal sufficient. This is basically, if you write it, let's call this, I don't know, CI. So what I would get is e to the eta I minus eta naught tx minus c1 up to e to the eta, sorry, 1 eta d up to eta d minus eta naught dx cd dot dot dot. I can write it like that, and I can further take actually the log. Let's take the log. This is also going to be minimal sufficient because the log is 1 to 1. So this is minimal sufficient. And then I can further write this as, so I gather all these as eta minus eta transpose dot 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 eta d minus eta transpose into a matrix. and then times t of x. This is, here is d by d, and this is d by 1. And then I add like negative c1, c2, cd, right? So now this matrix, this A is full rank. So you can see the connection with it. So full rank as a matrix. So what does it mean for a matrix to be full rank? Anyone remembers? Let's see if you guys are awake.
It's invertible.
Yeah, for this, they could square matrix. Equivalent to invertibility. In general, it means that the, for example, it has full column rank if the columns are. So here, the rows are independent, right? So by assumption, the rows are linearly independent. So that's where we use this construction. So the rows are linearly independent, hence it has full row rank. And because the matrix is square, it will have full column rank as well, and it will be invertible. So A is invertible. So A is invertible. Let's say this was a star. By star construction. So what is the significance of this? A is invertible. What can it conclude?
We can write t as a function of the minimal sufficient statistics, which means t is also minimal.
T can be, yeah, so T can be written at a minus 1 times that log p theta 1 of x. So that vector plus C, basically. This is C. So A is sufficient, and it's also a function of the minimal sufficient statistic. And in fact, it's like a mod-to-1 correspondence. So T is a function of the minimal sufficient stat, hence itself minimal. And you can see that if we couldn't find these, then there might be some issues. So you might be able to simplify further. So T of x. So that's the condition also that, as I mentioned, that's the E1 condition. If that E1 is violated, then you might be able to find a smaller, something smaller than Tx that's in one-to-one correspondence with this. But if the parameter space has this property that there is at least one point in the interior, then this conclusion follows. Okay. So pretty interesting, simple conclusion. So this shows that T of x is minimal sufficient for the subfamily, and because it's also sufficient for the full family, this P0 or P0 is just the set of this discrete submodel of the original model. So we're minimal sufficient for this and sufficient for the whole family. So T is minimal for P. Questions?
Are there restrictions on the function eta? Because if eta is just a constant function, then we don't necessarily have this full rank assumption.
That's a good question. So can anyone answer that question? So if we have eta constant, so go ahead.
I was thinking maybe that violates the linear independence in the first place. That was like one of our assumptions. So I don't know if.
So it violates one of these. So let's say if eta is constant, what would happen? What condition is violated?
E1 prime is violated.
E1 prime is violated, E1 is also violated.
Yeah, right.
Right, so the entire omega naught will be mapped to a single point, and a single point is not open in basically any of the RDs. Right, so E1 is violated, and so you could expect that the family is not. In fact, like any sort of trivial functions or constant functions would be minimal sufficient. Because so if eta is constant, your distribution does not depend on theta. Basically, you can't estimate theta. And you can just throw away your data. Just any constant function of your data would be as good as the entire data. So TOX is not minimal. Like a constant 1 would be minimal, something like that. Any question? Other question? This was a good question. Yeah.
Yes, Professor, I had another question. In Keener, they went directly and they assumed instead of full rank, they defined the curved exponential families, and they say as long as the etas didn't follow this linear constraint that you were talking about, they could still get the minimal sufficiency. So would that be another option in case we couldn't find full rank? We just show that these different etas don't follow a linear constraint.
Yeah, as long as you can. So if you go through this argument, so what you see is that as long as you can construct something like this, then you'd be fine. So even if it's full, if it's like, even if it's curved, as long as you can find a coordinate system like this. So suppose we are in R3, like on a helix or something like that. If I can find a place such that I can like figure out the point such that I can construct this sort of system such that the things are linearly dependent. As long as I have one point in my parameter space and these endpoints such that this is a three-dimensional, like it's linearly independent basically, or something like that, then this argument goes through, right? If you're in a line, then you're probably, let's say R2. If I have something like this, right, I can come up with two linear independent vectors. And so your argument, or I forgot where in Keener that does that happen. But as long as you're not on a linear, if things are linear, then you can find two different points such that they're linearly independent. But if you have a curve, generally you can't. So it seems like it's true. It's worth thinking about, is it possible to have some other curve such that this is violated? But it seems in general, as long as you're not, eta omega is not a linear or a affine subspace, basically. As long as it's not an affine subspace of our D of lower dimension, then it seems okay. Yeah, I'm not sure. I have to take a look at Keener. Is it a precise statement, or is it just an example? It's like a theorem?
Yeah, I think they were talking about if it's not curved, you won't get this minimal sufficiency, but you'll get sufficiency. But if you can show that it's full rank, you also get this completeness that you were talking about.
Yeah, but what I'm trying to say is that as you pointed out, you can also get at least minimal sufficiency from this argument. Yeah, full rank gives you completeness. I haven't proven that, but you can take a look at a more advanced book. But the minimal sufficiency, all you need is that you be able to, for example, if you have this curve, eta omega is this curve, as long as I can put eta 0 here, eta 1 here, and eta 2, and these two are linearly independent clearly in R2. Then this argument goes through and shows that the model is, or TLX is minimal sufficient. You can't further reduce TLX. However, if you are on a line, so this is eta omega, not in R2, then this argument will fail because you can't find this 3 set of points such that eta naught minus eta 2 and eta naught minus eta 1 are linearly independent, right? So once you understand the argument, you should be able to also argue the curved case in general. Okay. It was a good question. Are there other questions? Okay, so you can use this result, although we didn't prove it in its full strength, but this is the main source of complete statistics that we used in class. So most of the examples, if you go back there, examples of exponential families, and the sufficient statistic there is complete because the family is full, right? Okay, so now going back to the definition, this parameterization is in general allows you to map any abstract space, parameter space to RD, and then build a probability distribution. And I'm going to give you examples where you can construct distribution and spaces that might not look that familiar. So if you're in RD, you have addition and subtractions and things look nice. But if you're in a more abstract space, how do I even define a probability model on it? And this gives you a very simple approach, as long as you have a well-defined or nicely behaved way of mapping your objects to RD, whatever they are. Then you could define, let's say, distributions on it. But there is a natural parameter in this case that I can reparameterize whatever that parameterization is. I can reparameterize in terms of this eta and call this a new parameter. Equivalently, I can just consider eta theta that are equal to theta. So instead of starting from my abstract space, I think of maps already. I'm mapping to RD already, and now I'm renaming the parameter to be theta. So either way, you can think of this is called the case of a natural parameterization or canonical parameterization. So instead of working with that parameterization, we just work with this natural parameter. Oftentimes the properties of the family are easier to understand in this case. And this is going to be in general in general, the parameter space in this case is called the natural parameter space. So if your parameterization is the natural parameter, sometimes called canonical parameter, this parameter space that we define, called it actual parameter space there, now it's going to be called natural parameter space, or canonical parameter space. And it would be a subset of RD, not some abstract space. So this removes one, let's say, choice or one degree of freedom. Let's call it degrees of freedom, but one, let's say, one of the let's say parameters or one of the ingredients that were up to us to choose, which was this eta. If I just work with the natural parameter space or natural parameters, this is just going to be theta. So all I'm left is to determine t and this h or h dot nu basically. So as long as you define the sufficient statistic and your underlying measure, then you define the family. And for example, you can think of the case where your sample spaces are, your probability measure is nu. Nu is like the Lebesgue measure, or a rescaled version of the Lebesgue measure, or something like nu is h of x times the Lebesgue measure, or something like that. H could be 1 or something like that. Then the canonical exponential family these sufficient statistics, so let's say use just the Lebesgue measure. So I fix nu as the Lebesgue measure. I fix t as the map that maps the reals to x and x squared. Okay, and then my exponential family would look like this. So this has density. This density is respect to Lebesgue measure, and the log partition function would be this, and it's going to be finite if and only if you can verify, if and only if theta 2 is negative. And so the natural parameter space would be this. So without knowing the Gaussian, I have defined an exponential family distribution. And this turns out to be the 2-parameter Gaussian family. So if you didn't know the Gaussians, you can think of the Gaussians as the 2-parameter exponential family defined R, give it with this given, with this sufficient statistic. So it's the natural exponential family associated with this and the underlying Lebesgue measure. Okay, so if I change this to, for example, x and x3, I get a different exponential family, not Gaussian, but a different distribution, perhaps. I could like do x and I don't know, x sine x, for example. This would be a different family, and so on. Okay, does that make sense? You can just integrate this and verify that this integral is going to be finite if and only if this is negative. And from comparing with the Gaussians, you can see that the theta 1 and theta 2 are related to the usual parameters like this. So this indeed theta 2 has to be negative because you know that the variance is positive. But that also follows from this type of construction. So even if you didn't know that this was a variance, you knew that the integral has to be finite. So theta 2 has to be negative. Questions? Okay, so there is another example, which is I would like to skip in the interest of time, but I'll encourage you to take a look. So you can think of the multinomial as an exponential family in canonical form defined on this sample space, the set of all positive integers, d-dimensional positive integers, such that, and then I put a measure here that has this set up the x, h of x to be this with respect to the counting measure. And then the canonical family would be like, then t of x would be this. So the canonical family looks like this. Once you do this, then you'd show that in order for this to sum to 1, the partition function has to look like that. And then in this case, you can verify that, for example, this is not a full rank model because the components of this, for example, under this measure satisfy a linear or an affine constraint. So this violates E2. And so this model would not be identifiable. So these thetas would not be identifiable. And then you can try to reparameterize in terms of the new parameters like associated with the original. So this is the original form of a multinomial. That would put some restriction on the parameter. That model also violates one of these assumptions, violates E1. So, I'm not going to go into details. Just look at this if you are interested. Try to figure it out. So a multinomial distribution is an example that you can write as an exponential family, but there are some issues. So either E1 is violated or E2 is violated. And the canonical parameterization is interesting, but there is an issue with it. Okay, I'm going to skip this. Okay, so I want to spend some time on this one. So any questions so far? Except for the multinomial, which we didn't cover that carefully. Is the idea of the standard family, canonical family, fine with people? Okay, so let me give the more interesting example. Suppose we are now in R to the P, and my underlying measure, this is like the combination of h and nu, is the Lebesgue measure. And I form a sufficient statistic. It contains all the coordinates and all the pairwise sort of interactions. So this gives me, and then all the xi's squared. So this gives me all the, let's say, polynomial or monomials of degree at most 2. So x1 up to xp, x1, x2, x1, x3, and so on, and then x1 is squared, x2 is squared. So I map a vector in Rp to how many there are. So p plus p choose 2 plus p. So you can compute how many there are. So there would be, I'll let you figure it out. So that would be the dimension of the family in general. And then there is an associated parameter, canonical parameter associated with every coordinate. I'm going to write it as theta I for these, capital theta I for these, and twice theta ij for these. And the 2 is just for convenience, let's say. So I have to associate one parameter, canonical parameter, to every coordinate by the standard form, because that's the canonical. That's how a canonical exponential family is defined, or the density is defined. And then once you multiply out, you get an expression like this, okay? And this turns out to be the multivariate Gaussian. Okay, so the multivariate Gaussian is the canonical exponential family associated with this sufficient statistic. All the monomial moments of, not moments, but polynomials of degree at most 2. And then you can write this in a little bit more compact fashion using some matrix notation. So this part I can write as the inner product, theta and x is a vector. So x is x1, x2 up to xp. And this one I'm writing is as the inner product of a matrix times another matrix. And the inner product for these type of objects is defined as the trace of theta times this. So these are symmetric matrices. For 2 symmetric matrices, or in general for 2 matrices, I can define the inner product as A transpose B, the trace of A transpose B, which turns out to be just the summation of all the entries. So the summation of the product of all the entries over all I and j. And if they're symmetric, you can drop the transpose. So these are symmetric. So the inner product, this is the inner product, assuming the matrices are just vectors, giant vectors, the Euclidean inner product. And so using that notation, I can write this term as the inner product of this theta matrix times actually these 2 terms together. These 2 terms together, I can write this as the inner product of theta with x transpose. This would be this term, and this would be this term. So I'll let you verify this. And the reason why we added 2 is because of this. We wanted this to look like that. So you'd use the properties of trace and verify that you can write it this way. So this is a compact way of writing a Gaussian, multivariate Gaussian in canonical form. Okay, and the question is that what is this function? What is this log-partition function? That log-partition function is something that makes this whole thing integrable. And in general, it's going to be difficult to compute, but we can do a trick and just compare it with the density of a multivariate Gaussian. So you know the density of the multivariate Gaussian, and if you expand it, you get these terms. So this would be corresponding to this, and this term would correspond to this, and this part corresponds to this guy. And by comparing, you can figure out what the what these parameters have have to be in terms of the original parameters of the Gaussian. So theta would be something like that. This theta matrix would be related to the inverse of the covariance matrix, which is called the, so sigma inverse is called the precision matrix. Precision matrix. And A theta, you can write it in terms of sigma and mu, and you can rewrite it in terms of the canonical parameters. Okay, so that's the form of the A. And then by comparing these, you can figure out what the natural parameter space is. So the natural parameter space is a set of all theta and theta such that A theta is finite. So if you look at these, so anyone can tell us what would be the natural parameter space in this case, given the properties of the normal multivariate normal distribution. Let me ask you guys, was this clear so far? So you can view a multivariate Gaussian as a canonical exponential family with associated with this sufficient statistic and these canonical parameters and the relation of the canonical parameters to the original parameters via these interesting maps. So if you know something about the multivariate Gaussian, so you know something about sigma and mu. So what are restrictions on sigma and mu? You can translate those restrictions to theta and little theta and big theta. And so you can figure out what the natural parameter space would be. So can theta and capital theta be anything that I want? Or is there a restriction?
Capital theta has to be positive definite.
Yes, so it has to be positive semi-definite, exactly. So this is actually not positive semi-definite. It's the opposite. It has to be negative, positive, or negative. It has to be negative, positive, or not. Negative semi-definite. Because sigma is positive semi-definite, sigma inverse is positive. Well, actually, not semi-definite. It has to be a strictly negative definite. Can't be. So it has to be negative definite. This is like the condition that, so in the univariate case, if you remember, we had theta 1 and theta 2, and the condition was that theta 2 has to be negative, strictly negative. So this theta 2 was related to the, was in relation to the variance, and so this guy is related to the inverse covariance, and there's a negative sign. So because sigma has to be positive definite, theta has to be negative definite, and this is the only constraint because mu can be anything, and so sigma inverse mu can be anything. So we don't have any constraints on little theta, but you have this constraint on theta, capital theta. Okay, any questions about this? So this is a nice example, and so this example, I want to say a few more words about this. Viewing the Gaussian in this fashion, especially in this canonical form, let's see if I can. So viewing the multivariate Gaussian as a canonical exponential family, family ties it to the idea of graphical modeling. So this form, so we have P theta and capital theta of X. Minus A theta and theta naught. This allows you to argue that, for example, if I represent the no, like the variables, I have x's, x1, x2 up to xp. Let's say p is equal to 5. If I represent it, if I represent the nodes as, the variables as nodes in some sort of a graph, then you can argue that this parameter, this canonical parameter, has this interesting property that theta I j is 0 if and only if xi is independent of xj given all the other variables. Maybe I should assign this as a homework problem. This is a classical result of the all other parameters. Just because this is related to the precision matrix, and this is known about the precision matrix, but this formulation allows you to do that. And in order for you to verify this, you just have to form this conditional distribution of basically pxi xj given, I'm going to write it like negative ij. So everything other than ij, you form this, and then you show that this conditional distribution sort of does not depend on this part. Or you can actually write it this way, and then show that this factorizes into, let's say, the marginal of this plus the marginal of this guy. This form should allow you to do that. So they're going to be conditionally independent if and only if something like this happens. This actually means, sorry, this is not what I wanted. This means these two are independent. What you want to show is like this. You want to show that this factorizes like that. Pxj given minus ij. So you want to show that, so this means that they're conditionally independent given the rest. And you can use this formula to show this. And it's cited as a homework problem. So what you end up doing is whenever you have ij0, you would skip putting an edge. Whenever you have theta I, let's say theta 2, this is non-zero, you put an edge. So this is theta 1, 2 is 0, and so on. So I might end up having something like this. And so the interesting thing is that once you have this, this gives you, if for example, there is no edge here, you know that the meaning is that x1 and x2 are independent given the rest. So this graph encodes that. But once you have this, you can read off more conditional dependencies from the separations in the graph. So for example, if I condition on these two, because there is no path from this side to this side, then I can conclude that x3 and x1, 4 are conditionally independent given x2 and x5. So this is not obvious, but this follows from general graphical modeling. So the idea of graphical model is that you can encode conditional independence properties of a distribution in terms of the separation properties of a graph. And this is very useful for modeling and understanding multivariate distribution. And so this format of a or this form of a Gaussian multivariate Gaussian as an exponential family in canonical form, ties it to the idea of graphical modeling, because this canonical parameter has a natural association with how you form a graph when you try to model this as a graphical model. So the multivariate Gaussian is both an exponential family and a graphical model. And sometimes when viewed as a graphical model, it's sometimes called the Gaussian Markov random field. So there's a whole literature on these things. And this is one of the examples of a basic distribution, which is both an exponential family and a graphical model. Okay, any question, comment? So I just scratched the surface of this. There's a whole like course you can teach on these things. So if you're interested, I think some of the courses, Professor Ching probably, in one of his courses teaches about graphical modeling, and there are other courses, I guess, on campus or in our department that talk about this graphical modeling. So this is a whole area, just briefly mentioned it. Questions, comments? Okay, you guys are quiet today. It seems like either very clear or not clear at all. So feel free to interrupt. So this idea, like verbatim, you can translate it. So suppose I have this, but my original parameter space is not RP, but a discrete lattice. So let's say I have X, which is 0, 1 to the D. It's like a binary cube. The measure would be the counting measure, but I'm going to use the same statistics, the same mapping. That would give you another graphical, another exponential family in canonical form. And by comparison with this, you might imagine that that would also be a graphical model. So that idea, if you pursue it, leads to this idea of the Ising model. So this is another example where it's both a graphical and exponential family. So this can be, so if I do, so X be 0, 1 to the D, new the counting measure on X, and then P theta, or sorry, T of X be X for I from 1 to D, and Xi, Xj for I less than J, less than or equal to D. And I can try to include Xi squared, I from 1 to D, but because I'm dealing with binary variables, this part is just vacuous. I can just ignore this because this gives me the same as this. So including these would not be necessary. So that would be my sufficient statistic. And so the model would be P theta of X, X sigma theta I Xi, I from 1 to D, and then plus, let's say, theta ij, I and j, in D, xi, xj, minus a theta. I'm just going to write theta here, or you can write theta and capital theta if you want. So again, there's a matrix here that determines conditional independencies, so things being 0. So you can write down a graphical model. And there are extensions of this where instead of looking at all these statistics, I might just look at all of them in a graph. So as long as they're edges of a graph on these nodes. So instead of including all, I'm just going to include all the terms that are that are given by an edge. And so this would give me different Ising models. So for example, I could have the classical cases that you have a lattice of points. So the graph would be this. So any node that's here is connected to all of the like neighbors in R2. It could be 3D, and then there's relation between this and all of the other guys that are neighbors to it via this. And there's no interaction, for example, between this and anything that's here. So there's no interaction between these two guys. So for these two, I don't include a term here. And this given the graph and this you can imagine different distribution, or you can think of this general form, and then the theta i's that are 0 would define this graph, just like we did for this one. So you can think of this version as the general form, and then some of the thetas are 0. You can constrain them to be 0. And if you constrain them to be 0, then this would be a subfamily. So the family, this is the exponential family, which would be a subfamily of this if you restrict yourself to a subspace of the parameter space of this. And so this gives you discrete Ising models, which are discrete analogs of the Gaussian random Markov random field. And they're very useful for modeling dependent. This is binary data, but you can also, so if you have a binary vector and you're trying to model complex dependencies among them, this is an example model that allows you to do that. There's has been studied a lot in statistical physics. There's a lot of information, interesting information known about it. So there are phase transitions, other stuff, cool stuff happens in this model. And then you can also extend it to the case where you have multiple labels, so extension to this would be called generally a POTS model. So there are extensions of this as well. Okay, so this is another example of interesting exponential family models that are also graphical models. Questions, comments?
Professor,
Yeah.
Previously, we could ignore the x squared term because we said that 0 times 0 and 1 times 1 is itself. In the generalized model, would we have to bring it back since we have different terms now?
Yeah, that would be great. So just think about it. It's not going to be encoded like this. So what you would do is, in that case, you would introduce these variables that are indicators. So you'd say ik. It would be 1 if xi is equal to k. So you turn it into binary variables, and then you'd work with these interactions. So you'd include, so basically for every level you introduce an indicator. So every variable turns into k binary variables, and then you have d times k. So then you form, you treat it as some sort of an Ising model, but with these. So basically every node and every level you could interact with each other in general. And so I encourage you to try to think and try to write it down in that fashion. So that's how you do it. Instead of, because these levels are not usually meaningful. So these are just labels. There are cases where you could think of the levels as meaningful. And so like 2 is really like twice 1, for example. Then it makes sense to define things in terms of these. But generally, when you think of these labels, like 2 is equally as good as 1, but they're just there to separate the levels. If that's the case, the POTS model is a case like that. So you can think of these as like very abstract labels, like omega, I don't know, delta, whatever. So there's no numerical let's say, significance to them. So then you map them to that. That's basically what the POTS model is. If you really have, let's say, there's this ordinal or numerical significance to these levels, then you wouldn't use the POTS model, you would use a different model. Yeah, that was a good question. Other questions, comments? Okay, so let me give you another example, which is also interesting to see how general these things could be. Suppose I want to design a probability model or family of probability distributions basically on graphs or networks. So this is an active area of research that the data comes in as graphs or networks, let's say, sometimes called networks. So you see, for example, social networks that are generated, for example, online. So you have like Facebook, that's a giant social network, or you can think of the your sub network within the Facebook. So something called ego network. You're the center of your ego networks, and everyone has one of these ego networks to some. If you go to some that you can collect these, and you can see you get a giant data set of data that each individual observation is a network. And you can do it for other online networks. There are other in other domains, like in biology, there are a lot of them. So the genes, for example, interactions among genes or proteins are encoded as networks. So two genes interact if and only if you put an edge if there's an interaction, otherwise you don't. So they're natural. There are situations that networks naturally arise, and you want to model these. So you might ask yourself how I can model that. One way is to represent these networks as adjacency matrices, as binary an approach. Represent a graph as an adjacency matrix, which is a binary matrix, and then try to model the binary matrix. You can use these ideas, for example, if you want. Now you have a binary matrix. You can think of it as a giant vector. You can use Ising model, or you can do other things. So you can model a binary matrix in a different fashion. But there's also another approach, which is just treat them as abstract objects and then try to define functionals. So if I define functions from graphs to reals that are meaningful. So for example, you can define a function that counts, usually these are counts of various subgraphs. So it counts the number of edges, counts the number of triangles, number of stars of certain kinds. So say a star like this. And also, for example, the degrees, how many neighbors a node has. You can look at the average degree, for example, the property of a graph. Then if I collect enough of them, I can put them in a vector, and that would be my mapping from graphs to the RD. And then I form I form a canonical exponential family where the underlying space is the space of all graphs, let's say. And the measure is the counting measure. So it's just the usual measure on this discrete space. And so this defines a family of probability distributions, valid family of probability distributions, and A theta would be, you have to count basically, or sum over all of these graphs. It's not easy to find the log partition function, but this defines a valid model, and you can do inference on it. You can think of doing sampling on it. You can use MCMC methods like Gibbs sampling and stuff. And this just gives you an interesting way of defining random graph models. These are called exponential random graph models. And so, for example, Professor Hancock has, and his group work a lot on these. There are issues generally with the ARGMs. There are the degeneracy problems. If you're interested, I encourage you to go read about them. But that's just an example of how you can design exponential family models on the spaces that might not look like an Euclidean space. So they don't, graphs don't naturally add up, or You can't form linear combinations, but you can form these functionals, subgraph counts, and then now you're working with a vector in RD, and then you form this exponential family, and so on. Okay, sounds good. Okay, so let's move on then. So back to the full rank canonical exponential family, which I'm going to use this mnemonic for it, again, not standard. So we're now going to go over some properties that a general full rank canonical exponential family, this also means natural, let's say natural parameterization. What I mean by canonical is that we're dealing with the natural parameterization. So a full rank canonical exponential family has interesting properties. The first property is that A is going to be convex. So this function, log partition function, that appears sorry. There's this log partition function here. That log partition function is, so again, the parameter space is subset of RD. So A maps some subset of RD to RD. So this multivariate function is convex on its domain, which is omega naught, the set of all theta such that A is finite. And this domain itself is a convex set. And this is a consequence of the Holder's inequality. And I believe you're going to prove it in your homework, or you could do it as an exercise. So there's enough hints here that you can go through this yourself. I'm not going to go over the proof in the interest of time, but this is a very useful property. So some of the interesting, for example, if you go back to this is a very complicated function, multivariate function. It's saying that this function is jointly convex in little theta and capital theta, which is not at all obvious if you try to directly prove it. But as a consequence of that result, you get a nice source of convex functions. So any exponential family you construct, the log partition function is going to be necessarily convex. So this is interesting for convex analysis and statistics as well. The next proposition, which is also interesting, is that in a full rank canonical exponential family, A is C infinity on the interior of the domain. And C infinity means that it's differentiable and the derivatives are continuous. And this holds for all orders. Infinity means all the derivatives. And on the interior of the domain, which is non-empty, by the way, because of the assumption, A is going to be C infinity, basically smooth, very smooth. Moreover, the gradient and the Hessian, which is the second derivative, give you the expectation and the covariance matrix of the sufficient statistic. And this is very useful. Connects the differential properties of A to the statistical properties of the sufficient statistic. If you expand this, basically this is saying that the partial derivatives of A with respect to theta I are the expectations of the coordinates, and the second order partial derivatives are the covariances between the elements of T. Any question about this? Okay, so I'm going to try to prove this in the next couple of minutes that we have left. So the idea of this is to start from the moment generating function, which by definition for a multivariate, so T is a multivariate random variable. So for a multivariate random variable, the moment generating function is defined like this. So you take the e to the inner product of u with t, where u is just a parameter. So the moment generating function would be parameterized by u, which is in RD itself. And if you expand this, you can write this integrated against the density. So this is how you write down the expectation. And if you do this, then you recognize something you can simplify. So anyone recognize how we go from that line to the next? So this part, e to the negative a, is just there. What I'm claiming is that the other half, e to the u plus theta tx d nu tilde of x, this can be written as e to this. Anyone remembers? So if you go back to the definition of the log-partition function, this is exactly the definition. So we're just evaluating this log-partition function at this new parameter. Okay, that's the interesting part. And the log of this, in fact, is going to be this deviation. The log of this is called the commutant generating function, the log of the moment generating function. You can see it's related to a. That was another name of a. Okay, so this is the calculation. And there is this general result that if theta is in the interior of the domain, this is not the general, this is the assumption. If the theta is the interior of the domain, then m is finite in a neighborhood of 0. The reason why it's finite is because this is finite. If I take u small enough. If I take u small enough, u plus theta would be in the interior by the definition of the interior, because theta is in the interior. I can make u small enough such that this is in the interior, and being in the interior means that this is finite. And so the moment generating function would be finite in a neighborhood of 0, basically. So fixed theta in a neighborhood of 0, u is small enough, this is going to be finite. And then there's this general result that if this holds, if the moment generating function is finite in a neighborhood of 0, then the dominated convergence theorem implies that the moment generating function is C infinity in that neighborhood, or in a neighborhood, maybe a smaller neighborhood. Moreover, you can interchange the differentiation and integration. So this fact allows us to easily differentiate under the expectation. So that's the formula. And then you differentiate once this side and also this side and move it inside the expectation. So if I take the derivative of this, this is the derivative of this, and on this side, you can verify that the derivative would be this guy, and you can write it in terms of the original. This is the mt, so that would be the derivative of the other side. And I move this inside the expectation, I get this, and if you differentiate, you get ti times that, and then you set, you evaluate this as 0. If you evaluate this as 0, this side becomes e theta ti, and this side becomes mt of 0, which is 1, and this just becomes partial derivative of a with respect to partial derivative of theta. So you've shown that the partial derivative of a with respect to theta is ef ti, and this proves this result, and the next one is also proved similarly. Okay. Yeah, there are some remarks here which I'm going to come back next time. But go through this proof yourself, try to do this calculation and just verify. The only piece that you're using here is like this technical result, which I'm not proving, but this follows from the dominated convergence theorem if you're interested under the assumption. Okay. I'm going to stop here. Questions, comments? Okay, so